Hello, everyone. In this video, I'm going to talk about shift table, which is a low latency learned index for range queries using model correction. I'm Ali Hadian from Imperial College London. So for range queries, it's natural to basically a proper choice to put the record, keep the record sorted on memory. And then we use an index structure which helps us find where the record is. We have classical indexes like v+3, and we have learned indexes, which are like a newer approach. And both of these approaches try to find where the data is on the physical layer and basically on the physical pages. The only thing is models try to use basically machine learning models to predict where the data is. And if you take a deeper look in all of those families of algorithms, both learned and v+3, they have two stages. Stage one is inference, where we run the model or run the index, and it points us to somewhere in the physical data layout, in the sorted data. And the second stage is once we do some local search or last mile search on the physical data to find the actual result. So in the inference time, we're normally not gonna get the actual result, because, for example, in v+3, it points us to the page that contained the data, but we need to do some search on that page to find the first record. And likewise in the learned indexes, because we have errors, we just get a predicted position, and we need to do some local search to find the actual position. And both the inference and last mile search incur some memory lookups. Some of them could be cached or not cached. Learned indexes try to fit the model in cache to minimize that time. But then they also have to keep the error small so that the last mile search is small. And that's sometimes challenging. To show that, we designed a micro benchmark. So we basically consider the case that, so in a learned index, basically once you have a prediction, we need to find the actual position. And we have a couple of options. If we have the error bounds of the model, we can do binary search, or if not, if you don't know the boundary, we can do linear search or exponential search. And then to show how it affects the performance, only the last mile search, we designed a micro benchmark where we had pairs of predictions and actual positions. And we varied this error between the prediction and actual position to see how the last mile search algorithms perform. And as we observed on a logarithmic scale, which kind of shows the steps of the binary search algorithm, for smaller errors, normally everything is in the same cache line, right? So basically the latency is small. But once the error increases, at some point, the latency is affected significantly. And as you can see, we're comparing, so we have 200 million records. And as you can see, if we have like an error around 10,000 records, even the fastest local search, last mile search, like binary search, will be slower or at the same, like have this almost the same time than doing an efficient binary search over the entire 200 million records. So 200 million records of fast binary search would be equivalent to only doing binary search over only 1,000 records. And that's only the last mile search of learned indexes, put aside the inference time, which adds to it. And the reason is, and here also is the cache misses, which shows the same pattern. And the reason is that binary search enjoys a lot of cachings for the first few iterations, but learned indexes don't, because they start from an arbitrary position. So learned indexes are very sensitive to error, and the error has to be minimum. And at the same time, the model has to fit in cache. That's very easy on synthetic distributions. Like, for example, in this case, it's a CDF of a normal distribution. As you can see, for those mathematical distributions, they are derivable. So once you zoom in, it becomes a straight line. And it means that if you don't have too much information, it's very simple to model it with a very small model and then have a very low error and a very low latency. But on a real world distribution like this, we have a lot of fluctuations. It's a lot of information that if you want to model it efficiently, then we're going to have a large model. Or if we have a small model, then we're going to have a large error. And at the end, we're going to get a very high latency. So in real world distributions, learned models are not very efficient. What we suggest here as an alternative is to have an additional layer called shift table. And that shift table is handling those fluctuations on the data which require a very big model to learn. So instead of that, we have a small model and an algorithmic layer called shift table, which only takes one additional memory lookup, but it saves us a lot of error and latency. So here is how it works. So we have a model. So for example, we have 100 keys and keys from 0 to 1000. So we use a simple model where the key is divided by 10. So basically, for example, if the model is 770, we can say divided by 10, it's 77. What shift table is capturing is what's the shift of error. For example, here, it says we have an additional layer called shift table, which says if your model has predicted the key to be in position 77, you actually have to go back 41 records, and you will find it there. And we also keep another number called C, another value, which is like the count. So it means that because we have two conflicts, two keys pointing to the same position, if you want 41 rows back, then you still have to scan an area of size 2. So with this, it's a very efficient way to model these errors in the, it's a very efficient correction, and it only takes one memory lookup. Here is a very simple case where we use a very dummy model called interpolation. It just does one interpolation and then uses it as a model, which is very stupid. Like you can see how different it is from the CDF. But if we add shift table to it and correct those shifts, the shifts are huge, but it corrects it very efficiently. And the eventual error of using this model plus shift table, if we do that, the error is going to be really small. It's going to be around 10 records, 5 records, or for most records, it's going to be around 0. Like it actually points to the record. And that's really good. So we tested it on the benchmark for learned indexes called SOSD benchmark. And what we observed is that, so by default, the learned indexes do really well for synthetic datasets and relatively good for real-world datasets. But once we add this shift table to both to the learned index and to some even very simple models, we can see that the performance is, the latency is improved significantly, and we actually outperform the best learned indexes by roughly 2x, which means we have a latency that is half of the best of the learned indexes. So, and also if you see, we got the best performance for learned index on a very simple model, which we explained here. So basically, this very simple model is actually here giving us the best performance for most data sets. And that's really good, which means we don't need training for, we can use very simple models plus shift table and get very low latency values. So in summary, our conclusion is that learned models are for modeling, not for overfittings. We have to use them only for capturing the generic patterns in data. And the fluctuations in data, which requires a lot of information, theoretically, a lot of information to be learned, that can be delegated to an algorithmic layer, which only takes one memory lookup, and it handles those fluctuations really well. And by using this simple trick, we got a latency that is 1.2 to 2x faster than the best of the learned indexes, which is usually RMI. So we got a latency that is 1.5 to 2x smaller, basically, in terms of latency than RMI. And in future work, we're gonna think about how to support updates in the shift table. Thank you very much.